So today we're going to finish our solution for the hydrogen atom, which is probably the most dramatic success of quantum mechanics. And so here is our solution. So again, we have a separable solution of a radial part. The angular part we've already talked about. And so today we're going to figure out and finalize the radial part. Now, what I'm going to do here is I'm going to go through and just kind of talk about some of the important aspects of these solutions. There's another video that goes through the nuts and bolts of solving this differential equation, which is kind of a beast, and so I just don't want us to miss the big picture. So right now we're just going to kind of focus on these solutions a little bit. Now, to reiterate, what we're doing here is we're solving the time-independent Schrodinger equation, which turns out to be an eigenvalue equation. So our goal is to go through and find our solutions, which are these guys here, as well as the energy eigenvalues. And what we did is we separated this equation several different times, a couple times, and so here is our radial equation. So again, in the other video we show you how to solve this differential equation. Right now we're just going to say, okay, we solve it, and we get a radial solution where we have two quantum numbers that specify each one of these functions, n and l. And so if we go through, so again, this here, we would call these guys our energy eigenfunctions. I should be careful. The energy eigenfunctions, these are the radial parts of the energy eigenfunctions. And then here are the energy eigenvalues. And so you've probably seen this equation before. This was actually found by Bohr in his simplistic model of the atom. And what's really great about going through and finding this from the Schrodinger equation was to derive this from a fundamental equation of motion, the Schrodinger equation. So that was the really important thing, to start with a really more fundamental idea and to find this. So again, we have three quantum numbers. So n is our principal quantum number, and n goes from 1 to infinity. And so there'll be an infinite number of these radial solutions, infinite number of these energies. L, we'll get more into this next time, is our orbital angular momentum quantum number, and L can go from 0 and then by integer values for the orbital version up until n-1. Now in the other video we show where this comes from. Here we're just trying to make sure that we're clear about this, because this will be really important to us moving forward. And m, which we've mentioned a few times, is often referred to as the magnetic quantum number, and m depends on the L value. So it can carry any value from negative L by integer increments. So negative L, then like negative L plus 1, dot, 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 to L minus 1 to L. So it can go anywhere from negative L up to L, going by integer steps. So here are the first couple of the radial part of the eigenfunction. So again, R sub 2, 0. So if we just look at this, we can just sort of see how this works again. So for n equals to 1, this top one over here, we have one function, L equals to 0. That's the first one up there. For n equals to 2, L could be either 0 or 1. And so we've got the R2, 0 and the R2, 1. And then for n equals to 3, L could be either 0, 1, or 2. So these are how the first three sets of these play out. You can keep going as you want. These functions have a name. The associated Laguerre polynomials. Your textbook goes into this a little bit, but just to kind of give you a heads up about that. Here is a plot of the first couple of these. Now I got this just to get some nomenclature. There's different ways to name these. This is sort of how important these things are. They have different kinds of names. You can sort of tell how important something is by how many different names it has. So for our L equals to 0 state, which if you go back here, right, each one of our n, 1, 2, 3 has an L equals to 0 state. We call that the S state. And you can think about that as S as being the spherically symmetric. So L equals to 0 will be our spherically symmetric states. If L equals to 1, we call these the P state. These names are pretty much historical, so I wouldn't worry too much about them, but just so you'll probably see things written in different ways. And then L equals to 2 is the D state. It keeps going on, but we'll just sort of focus on these couple of them here, just sort of talking about this here. And so again, our total wave function is going to be the radial part, and then times our spherical harmonic part here. And this is a plot of R as a function of R. So a couple just notes about this. So the first thing is you'll find that these radial functions go as R to the L power. And so what that means is R typically goes to 0 when the R coordinate goes to 0, except for the S states, the L equals to 0 states. So you can see that over here in these plots. Okay, the 1s, the 2s, the 3s, all are finite at R equals to 0. So these plots here are done as R versus that Bohr radius, the A. Sometimes it's called A, sometimes it's called A0. Another thing to note here about these is that there's a number of nodes in these things, which will sort of be important just so we can kind of see a picture of what this means. So there's going to be n minus L minus 1 nodes in each of these functions. And so we can go through. And so we can see here for the 1s state. So this would be, this state is n equals to 1 and L equals to 0. So if I look at that equation for the number of nodes, n minus L minus 1, I get 1 minus 0 minus 1. So there's 0 nodes here. Whereas for the 3s, so this is n equals to 3, L equals to 0. So I get n minus L minus 1. 3 minus 0 minus 1, I get 2 nodes. And you can see, so there's 2 points where this radial function goes to 0, which of course when you square this function to get a probability density, that means there'll be no probability of finding it exactly at that point. I'll say we'll probably spend a lot of time just trying to visualize these functions. It can be difficult. We'll find a lot of different ways to do it, but this is just our plots of this radial function. Now, if you remember, that's the radial function, and here's our spherical harmonics, the angular part. So our total function, which we're going to sort of spread out now and sort of try to look at these here and connect all this. So again, this would be our energy eigenstates, the full energy eigenstates, and this is again our energy eigenvalues. So just like we did in one dimension, we took the time-independent Schrödinger equation and solved it. It was just much longer of a process this time. Now, one thing we will talk a lot about is just the degeneracy of these states. And so again, each state is specified by an n, L, m, these 3 quantum numbers. So the m, as we were talking about, goes from negative L to L, or can go, by integer values. And so the way that it works is for each L, all right, there'll be 2 times L plus 1 states that you can have. So for instance, if we're in an L equals 1 state, then the m can go from negative 1 to 0 to 1. So that's 3. And so of course that's 2 times 1 plus 1 equals 3. And so that tells us how many, so for each L equals 1 state, or for the L equals 1 state, there's 3 states that go along with that. And so we can look at, just make a little chart here. And so we'll say this will be our principal quantum number n, and then our L, and then the number of degenerate eigenstates, which we're going to find will be n squared. So for instance, for the n equals 1, the ground state, there's just one possibility, that's the 0. And so we have just one state with that energy. This is, of course, excluding spin, which we'll get into eventually. N equals to 2, you have 0 and 1 as the possible values of L. Now if I take this little guy here for my formula, so for the 1, I get 1, or for the 0, when I plug that in for 0, I get just 1. For the 1, I get 2 times 1 plus 1. is 3. So I get 1 plus 3 equals 4. So there's a total of 4 states with the same energy for the n equals to 2. So again, that's n squared. And just the last one we'll do, you can work out the rest yourself. So n equals to 3 would have L equals to 0, 1, or 2. So in this case, the 0 has 1 state. The 1 would have 3 states, and the 2, so 2 times 2 is 4 plus 1 is 5, equals 9. So again, it goes as n squared. So that's the different kinds of degeneracy, or what we mean by that is, how many states have the same energy. Now, when we get into talking about perturbation theory, this will become really important, and it's kind of nice to just think ahead that, so this energy is neglecting a lot of smaller energy effects that we'll talk more about when we get to perturbation theory. So again, we've solved for the full hydrogen wave functions, the full hydrogen energy eigenstates. They're these guys here, and just like with everything else, because it's 3 dimensions, it's going to be a little bit more complicated. So the general principle would be that we want, if we integrate over all space, right, we want this to be normalized to 1. So we've talked about this. The way that we do this in practice is we normalize the radial and the angular parts separate, but the overall integral will look like this here. And just remember that our volume element is a little more complicated when you're in the spherical coordinates. So going back to stuff we talked about in 1D, the probability density is this guy right here. So the probability density would be the psi NLM absolute squared. And so that's like this. And that's going to have units of probability divided by volume. Now, one thing to know, I think we've mentioned this, but there is no phi dependence, which you'll also, again, sometimes see as no azimuthal dependence. So when you take the absolute square of the psi LM, the phi part cancels out completely. So just keep that in mind. A lot of the pictures and visualizations we'll have will reflect that. So again, probability density, which I'll define this way here, is psi squared. And what that is telling us is that the probability per volume of finding the particle at a particular point, and our point would be specified as r, theta, and phi. So you got to be real careful with our definitions here. Now, if we look here, so you can look back at the charts that I've shown or in your book and get these 2 different functions. So the radial function, so let's just look here at the ground state. So we're talking about NLM is 1, 0, 0. We get 2 over a to the 3/2 power e to the negative r over a. And the spherical harmonic in this case is really simple. There is no angular dependence at all. It's spherically symmetric for the L equals to 0 states, as we've mentioned before. And so when we put this all together, this here is the wave function for our ground state of hydrogen. And what we can do then, of course, is take that and find the absolute squared, which would be something like this here. So for your visualizations, your textbook will generally have something kind of like what we have here. It's difficult to visualize this because your psi is a 3-dimensional function, right? And so what we're trying to do here is we're trying to find a way to visualize probably the most popular thing people look at will be the probability density, which is again a probability per volume, and what that means to us is it's our psi squared. So that, in theory, is a 3-dimensional beast. And so you get pictures like this here. There's a 3-dimensional space. So here we've got all the x, y, and z axes, and you're just looking at a dimensionless axis. So it's just it's the position divided by a sub 0, which is the Bohr radius. And in these pictures, what we've done, what they generally do is basically the brighter spot would be the higher probability. And what does this mean? Well, if you take like a little box of volume dV, the probability density would be the probability that your particle would be found inside that box. And so here, if you just move that box around, sort of the higher brightness would be where it's more likely. And of course, this is a two-dimensional slice of what is really a three-dimensional thing. And for us here, what we've done is this is this picture for the ground state. So again, the ground state is spherically symmetric, like we were talking about. There is no angular dependence. And basically, if you look at those plots we were looking at before, like this here, this r sub 0, what this is basically it's really high at the origin, r equals to 0, and then sort of dies out exponentially as you move out from that. I also wanted to briefly mention another way that you'll see this represented. So here's the nice plot we were just talking about of the radial function as a function of r. You also see this here where you're looking at the radial function r squared times the absolute square of the radial function. And so this thing is called the radial probability density. And so let's just explore that a little bit. So here's, again, this is our function to find, the normalization. So this hopefully should all equal 1. So if we take our particular wave functions, all right, and set them up, we'll end up as something looking like this here. So we have one over here, one integral, which would be r squared, r n l r absolute squared. So that's basically the radial part. And then we have the part that would end up being the angular part. Like so. And that would include the sine theta, d theta, d phi. Now, if you remember, we separately normalize these. So this whole function here, no matter what the YLMs are, this is normalized to be equal to 1 if we go over all space. And so if we set this up then, what we can look at here then is just our normalization requirement essentially for the radial part. But if we sort of look at this together here, this is what we call the radial probability density, and then this would be our dr. And so what does this mean here? Well, again, this is the thing that we're plotting in this picture here. And so the radial probability density, so if we think about a three-dimensional picture where this is, the proton, then if there's some spherical shell of radius r, okay, this r squared, capital R squared, basically tells us the probability of finding your particle in this spherical shell. And again, the thickness of this spherical shell would be dr. So the total sort of probability would be this times dr is the probability of finding the particle inside this spherical shell. So it's a different thing you're looking at than this over here. And it's the radial probability density versus just the radial function. So you'll see these pictures. They can all be kind of instructive. I just wanted to kind of show and explain that difference a little bit. Here's a picture of some more of these. And you can see that with the radial probability density pieces over here, right, you can see here are these nodes we were talking about before. And so you can kind of get this sort of picture that you're much more likely to find the particle in a spherical shell here and here than here. And you can kind of sort of see the structure that you get as you get to the larger radial functions. Again, just different ways to visualize this. Your book has lots of pictures, and I also encourage these days with the internet, there's lots of little places and pictures and apps and things to help you visualize these things. And finally, finally, the last way to visualize these things are these plots here. And so here we've got essentially what we had done before, a plot of the probability density. Here we got the ground state, the 1, 0, 0, and then we've got the n equals to 2 states, so 2, 0, 0, 2, 1, 0, and 2, 1, 1. And so these are again, the idea here is that the brighter it is, the more likely you are to find the particle in a little volume at that point. And so you can see here, like here's basically this evidence of the node for the 2, 0, 0 part. And when you get to the ones that aren't spherically symmetric, so again, the L equals to 0 states, which would be these guys here, are spherically symmetric. When you get outside of the L equals to 0, it's no longer spherically symmetric, and then you've got the radial function in tandem with these over here. So if you remember before, we sketched out a few of the angular functions and what their dependence was, and so you'll notice some connections there between, like you can see here, this guy sort of looks like this guy over here. Again, these are really difficult to visualize, but these pictures I think can be insightful and can be useful. Now these visualizations can be nice, but to say anything quantitative, we're going to need to go back and do some calculations. So here's an example of the kind of things we can ask. And so here's a problem. Find the probability that the electron in the ground state of the hydrogen is measured to be within 1 Bohr radius, again that's our constant A, of the nucleus, and calculate the expectation value of the radial position R. So let's do the first part of that. So we'll call that part A. Now if you remember, so here would be our calculation we'd want to do. So we're trying to find what's the probability the electron is going to be measured within 1 Bohr radius. And so if you look at our triple integral, so the angular integrals, I just did the full integral, and then for the radial part, I'm only doing from 0 to A. And again, that would be over our square root of our wave functions, both the radial and the angular part, and then this is our, again, dV. Now, if you recall, we actually looked at this one earlier, and you just gotta be careful. So the radial part of this one is 2 over A cubed, and then the exponential e to the r divided by a. So again, this is the ground state, and the angular part, the spherical harmonics in this case, is 1 over 4 pi. Now, for a problem like this, it doesn't really matter, because what we're going to do is we're just going to take, these angular parts here, this guy, and then these guys here, just realize that that's normalized to 1, right? So if you write this all out, you can write it out as 0 to a r squared. Now I'll just write this as r 10 squared dr, and then that's actually a times. So all that times by the angular parts of our integral. And of course these spherical harmonics are normalized individually. So this part just equals 1. And so the actual integral we need to do is going to be this guy here, r squared r10 absolute square of that dr. So these integrals, even just sort of setting them up when they're these triple integrals can be a little bit tricky, and so you want to get some practice doing that. When I went through and did this here, so we take the square of the wave function, and oh, be careful, this wave function is actually to the 3/2 power. And so when I squared that, I got 4 over a cubed from 0 to a, r squared e to the negative 2r over a dr. And when I went through and did that integral, I got a number 0.323. So what we're saying here is there's a 32% chance to find the electron within 1 Bohr radius from the nucleus. And then the other kind of calculation you can do is finding expectation values. And so here, this would be the expectation value. So we'd be actually calculating psi 110 sandwiched between, or an r sandwiched between the two psi 110s. And so we're just adding an extra piece of r in here. Now the same thing applies in that the angular part is not affected by the r, and so this whole piece here basically boils down to an integral looking like this right here, with our coefficients out front, 4 over a3. Now again, so there's 3 factors of r, 2 come from here and 1 come from here. So this is maybe an easier integral. This one, you can find this in a table pretty easy. So 0 to infinity of some x to the n, where you have e to the negative x, say, divided by some coefficient b. That comes out to be n factorial, and then b to the n plus 1 power. And so if we look at that here, so we've got our coefficients for a cubed outside, and then from this equation over here, I'm going to have 3 factorial, and then this factor of b, And our particular equation here is going to be a divided by 2. So you got to make sure you get that factor of 2 in there to the 4th power. And so if you look at that, that'll be 4 times 3 times 2 over a to the 4th, or a cubed, a to the 4th over 2 times 2 times 2 times 2. And so when I did this, I got 3/2 the Bohr radius. And so those are the kind of calculations you can do to be a little bit more precise. Here's a graph sort of encapsulating what we just calculated there. So if you look over here, so this shaded region here is actually between 1 Bohr radius. So again, when we do these plots, so this is the radial probability density graphed against r divided by the Bohr radius. And so this is actually the distance of 1 Bohr radius, 2 Bohr radius, so on and so forth. And so this was the actual probability we found, the area under the curve of again, this integral, right? Because the integral we did when we were finding the probability was, 0 to a of r squared, that capital R squared dr. And so that's that calculation. Here is the actual expectation value of r, which is oftentimes written that way there, which can come out at 3/2 times the Bohr radius. So these are the kind of things that we'll be calculating this weekend in homework.